make sure I say your last name right. Valbonesi.
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 Perfect.
Should I put a little Italian?
It's up to you. I think my accent is enough for the both of us.
That'd be awesome. We'll make sure the Italians see this.
Okay.
You should give a shout out to your Italian friends. Say, are we go time? Good morning. Once again, here we are at the ePMP Now session, broadcasting from Rolling Meadows office via a beach in Hawaii, I think is what's behind us. I'm very excited today because we're going to talk about a popular topic, and I have a special guest with us, Lucia Valbonesi. She is our, say hello, Lucia.
Hello, everybody.
She's one of our chief architects at Cambium Networks. And the topic we want to discuss today, Lucia, and which is why I invited you to the show, is the Cambium Sector Antenna.
Yes.
Which is what I have here. And there's a few topics that often come across from our customers as we talk to them. And that's about not just our sector antenna, maybe the technology behind the antenna, antenna characteristics and parameters that are important in the wireless business. And oftentimes we see that maybe we know the answers, but our customers can benefit from an explanation and a easier way to understand why it's important. So I would like you to go through some of those topics and share that with the customers.
Sure.
Before we start that, just wanted to, for everybody's benefit, this is what the Cambium 90°/120° sector antenna looks like. It's a 5 gigahertz antenna. If you want the specification for this, it's available on our website on cambiumnetworks.com. A few things about the physical aspects of the antenna. You'll notice that it's quite small in height, which is an advantage in terms of tower space, because bigger antennas potentially could cause higher rent when you put it up on the tower. The mechanics of the antenna has shrouds to protect against the environment when you put the radio underneath. This is compatible with both our ePMP access point series as well as the 450i access point. So therefore, this is the Cambium 5 gigahertz sector antenna. The specifications for this, we can pull up the spec, but more or less it's a wideband antenna. So it is going from the low 5.1 to the high 5.9 band, and different characteristics around consistency of the performance across the band. Null fill is what we're going to go through. But I highly encourage people to take a look at the specifications and information on our website for this antenna. Okay, great. With that, I'll put down the antenna, which, by the way, is a little heavy, and we'll explain why that is, too, in a few minutes. So, Lucia, one of the first topics that we emphasize a lot at Cambium Networks is the concept of front-to-back ratio.
Yes.
And we have videos that talk about it, but how would you like to give us a little lesson on what front-to-back is and why it's important?
So, first of all, I want to talk about the fact that this is a directional antenna.
Okay, right.
So what does that mean? An omnidirectional antenna would be an antenna that sends the signal strength in all directions.
Okay.
But the directional antenna focuses the energy in only one direction. And when you talk about directional antenna, there are really three things you look at: the main lobe, the side lobes, and the back lobe. So the main lobe is where you want your energy to go, is the one in front.
Is that me talking in a certain direction?
Yes.
So this is my main lobe, my voice, mouth is here?
Exactly.
Okay.
So if you imagine this location is your access point and all your subscribers are in front of you,
right.
This is your main lobe of what you want to illuminate because you're talking to the subscribers.
This is the most energy I'm sending in that
Yes.
direction. Okay.
And the better the antenna is, the more energy you send in your desired direction in front.
I see.
Then you would have the side lobes, which are separated by nulls from your main lobe, and you want this to be as small as possible because you don't want to send a lot of energy on the side if
Right.
all your subscribers are in front.
So let me ask you a question. This is my education as well. So I designed an antenna, and it's got energy in the main lobe. Why can't I design it so that there is no side lobes and no energy coming out anywhere else? Is that just a physics and an issue of building an antenna? Because somebody once told me that designing an antenna is like a balloon. right? If you squeeze it in one direction,
That's true.
right, there's always going to be something coming out of it.
Exactly,
Okay,
exactly.
okay.
That's actually a good analogy. So
Okay.
you're always going to have something in the directions where you don't want to send your energy. The trick is to design a good antenna so you can minimize the energy in the directions where you don't have your subscribers.
Right.
So you were talking about the front to back. The back lobe is 180 degrees in the other direction. It's
I
in
see.
the back
So
of
it's
the
behind me,
antenna.
essentially.
It's behind me. And I want the energy going in that direction to be as small as possible because my subscribers are all in front of me, right? So one parameter is the front to back ratio, is the ratio between the signal strength in front and the signal strength in the back. Now, this is important if you talk about frequency reuse and frequency planning.
Right.
If you're trying to reuse the same frequency back to back, for example, let's
So is this you and me standing with our backs to each other?
Yes, so I'm going in
And
this
talking
direction.
in each direction?
Right.
Okay.
So imagine you have a site with 4 sectors, and you want to reuse 2 channels in your 4 sectors.
Right.
You could have A, B, meaning that the back-to-back sectors both use frequency A, and the other 2 sectors, which are also back-to-back, use frequency B.
Right, right.
Now, in that case, if I'm facing this way, you're facing this way, and I have a lot of energy leaking in the back of my sector, then your subscribers will also hear my signal because it's
They're on
using
the same frequency. Right,
Exactly,
right.
exactly.
So for the audience, we're talking specifically front to back, but I think there's a lesson here in terms of the concept of frequency reuse. I think maybe we can have another session where we discuss what it means to have frequency reuse on a sector or on a tower or a wider geographic area, the implications. But for today's purpose, the takeaway is, if you're trying to reuse the same channel,
Yes.
back to back this way or that way in a 360-degree sector, the idea is if 2 antennas are sitting like that, the energy, the purpose of this antenna is to project the energy in its front, but there's always going to be some energy coming out the back. And if the other antenna is here, this antenna is also listening, and they will pick up some of the energy from the back.
So there are 2 issues. One is in the downlink and one in the uplink. Why won't we talk about both cases separately? Let's start with the downlink. Let's assume this is my sector, and I have one of my subscribers facing in front of me, hearing my signal.
Right.
Now in the back, there is another antenna facing the other direction that's using the same frequency
Right.
that has some signal coming from the back of that antenna.
Right.
Now because the 2 antennas are co-located, the 2 signals travel the same direction to the subscriber,
Okay.
which of course is at the same
Do
distance.
you think we could do a little visual on
Sure.
the board,
Absolutely.
maybe?
So let's assume I have 4 sectors, and
Right.
the idea here is for frequency reuse, we said this is sector, these 2 sectors back to back use frequency A, and these 2 sectors use frequency B.
Right.
Now let's assume this is my subscriber, and this is my antenna transmitting the desired signal
Right.
from this access point to my subscriber.
Right.
At the same time, I have another access point here, and there is some energy leaking in the back of this antenna going also in this direction.
Right.
So the attenuation between the desired signal and the interfering signal is only given by the front to back ratio of the antenna, because the 2 antennas, the assumption is that they are co-located and there is nothing in between.
Right.
Of course, if you had this installed on 2 sides of a building or 2 sides of a water tower,
You have enough isolation.
You would have additional protection because there is additional attenuation. But the worst case would be if there is no additional attenuation, and now this is your interfering signal. Now let's assume the antenna has a poor front to back ratio, something in the 20
Right.
dB. What happens? The interfering signal is only 20 dB weaker than your desired signal. So this prevents you from using a high modulation at the subscriber in this downlink direction, just because of your own, if you wish, interfering signal coming from the other sector. This is regardless of the distance of any other interfering signal you may have in the area. Just the signal coming from the back of this antenna would prevent you from using a higher modulation.
So very, very interesting and important point, that regardless of external interference,
Yes.
regardless of anything that is not in your control, the simple fact that if you have an antenna with poor front to back ratio,
Yes.
the implication is a subscriber may not achieve the highest possible modulation because its noise level is
Correct.
being increased by your own sector using your own frequency, but facing the other direction.
Correct.
But because it doesn't have good front to back, it's raising the noise floor. Okay.
And in the downlink direction, this happens all the time. Because think about the 4 sectors. These would be co-located and synchronized. So you will have a GPS synchronization.
They're all talking, listening at the same time.
Exactly. So their duty cycle is synchronized. When it's the downlink time for one access point, it's downlink also for the other. It means they're all transmitting at the same time. So when this subscriber is receiving the signal in the downlink, the other access point is always talking. This situation occurs all the time.
Right.
Now let's talk about the uplink direction. Now let's assume again this is my sector. I have my subscriber now talking in the uplink direction with this access point. I have another subscriber in the sector in the back also talking in the uplink direction here at the same time. Now this access point will receive the desired signal from the front and the interfering signal from the back. Again, the attenuation is provided by the front to back ratio. Now here, another consideration is the relative distance of the 2 subscribers with the tower.
Right.
If the 2 SMs happen to be exactly the same distance, then the only attenuation is provided by the front to back ratio.
Right.
If this subscriber happens to be farther out,
The distance helps.
the distance helps.
Right.
There is additional attenuation.
Right.
But if this subscriber happens to be really close, now the protection provided by the front to back is reduced because this signal will
And it
arrive
becomes even
stronger.
more important that front to back is high.
Absolutely.
In that case.
Absolutely.
So what you're essentially saying is, if I may draw this a little bit, this is a subscriber, and this is in the uplink direction.
Yes.
Energy from this subscriber is going towards that. You have 2 antennas here, and the front to back here causing this SM's energy to be heard by this subscriber as well as the back of that AP.
Correct.
Okay. Okay.
And in the uplink direction, things are a little bit more randomized because,
Right.
of course, both sectors will be scheduled. So when this SM is scheduled to transmit, it will not always transmit at the same time as this specific SM. So sometimes it will talk at the same time as an SM that's farther out, but sometimes it will be scheduled at the same time as an SM that's closer in. So the 2 schedulers are independent, which means, again, the front to back ratio is very important to protect the signal.
Great, thank you very much. So for our sector antenna, what is the front to back ratio?
So we have more than 30 dB front to back ratio. It's 35 in bore side, meaning right in, if you think 0 degree in front and in the back. And this allows you to go up to the highest modulation level because the protection is enough, even if you don't have any additional separation between the antennas.
I see. Excellent. Thank you. Thank you for that. Next topic, and maybe you can stay at the board and maybe erase that and we can start the new one, or we can also do a PowerPoint background. But this is an important topic. If we can have the camera back to the speakers here. The antenna we have today, when we offer this, we say that you can use this antenna both in a 90-degree sector as well as a 120-degree sector. It's a very common question. Why is that? How is it that we can use this antenna both 90 and 120? Please help us understand that.
So first of all, you need to know what the beam width of your antenna is.
Okay.
Let me.
Is there a PowerPoint slide that would
Yes.
help show maybe? Okay. Please go. Are we able to see the? Excellent. Okay.
So one important parameter is what we call the half power beam width, or simply beam width of the
Half
antenna.
power beam width. Okay. Beam width of the antenna. Okay.
This is the angle at which the gain of the antenna drops by 3 dB. 3 dB is half the power. That's why it's called half power beam width.
So tell me, the 3 dB is half the power.
Yes.
And what's the implication in terms of power? What does 3 dB mean? Why is that so important to have 3 dB more gain or less to a customer?
So everything comes down to the link budget between the access point and the subscriber.
So the distance I can cover and the modulation I can get.
Exactly. So the higher the link budget is, the higher modulation I can use, which means I can send data at higher throughput.
Okay.
When I quote the gain for the antenna, that's typically the gain at 0 degree azimuth, right in front of the access point.
Okay.
But if you look at the antenna pattern like we see here, we see that the gain slopes down, it decreases a little as you move in azimuth. If you move your angle
left and right, drops in gain. Okay.
So let's assume you have a 90-degree sector. So the case we saw before when we have the 4 sectors, each one is 90 degrees. If I have a 90-degree antenna, it means that at the edge of my sector, which is the plus or minus 45 degrees, the gain of the antenna is 3 dB lower than the gain I have exactly in front. So the SMs that are in front, assume they are all at the same distance for simplicity, they will have a 3 dB higher received signal strength, which may translate in higher MCS.
Right, and as well as that's doubling the distance, no, half the distance at 3 dB.
Correct,
Right.
exactly.
Right.
So every dB that you drop, of course the link budget goes down, and now you can sustain the same MCS at a lower distance.
Right. And at 3 dB you're half the power.
Correct,
Right.
exactly. Okay. So if you use this 90-degree beam width antenna, we said at the edge of, in a 90-degree sector, at the edge of the sector, the subscribers will have lost 3 dB in link budget or in antenna gain.
Right.
If you use the same antenna in a 120-degree sector, you can see the pattern keeps sloping down. So now at plus or minus 60 degree, which is at the edge of your 120-degree sector, now you will be down about 6 dB.
Right.
So if you look at individual SMs, now 6 dB, it will be even lower modulation, right? Lower MCS because the link budget is lower. So at the same distance, you can transmit the data at a lower throughput.
So what you're saying, since this is an interesting topic, is that I'm at a 90-degree sector, and at plus or minus 90, I expect the energy to be 3 dB less.
Yeah, plus or minus 45.
Yeah,
Yep.
I'm sorry.
Yeah.
Plus or minus 45, the energy is down by 3 dB. At plus or minus 60, the energy is down by 6 dB.
Correct.
So the question becomes that, so I can do a 90-degree coverage with this,
Yes.
no problem, because up to plus minus 45, I'm pretty good. After that, I'm starting to drop 3 dB.
Correct.
But if a subscriber is between my 45 and 60 degree, that means it's being served in a 120-degree sector.
Yes.
It's not, it's somewhere between 3 dB and 6 dB. So it
Correct.
hasn't really dropped down to 6 dB yet.
Correct.
Is that sort of the secret why we can serve customers at 120?
Correct. So the link can still be sustained.
Right.
You lose some additional dBs.
Maybe a
between
dB
3
and a half
6.
or a dB or so.
Exactly, depending how close you are to the edge of the sector.
Right.
You can still sustain the link, but each individual SM will have a reduced link budget depending on their specific location. Now the question is which antenna is better? What's the best scenario, right?
Right.
So in my mind, the important thing to consider is if you have an isolated sector, or
Right.
if you don't worry about frequency reuse.
So you're not doing this back
You're
to
not,
back.
exactly.
Right.
So if you think of just about one and don't think about that frequency being reused or interfering with anything, generally speaking, the wider your beam width, the better off you are.
Sure, because I
Right.
can cover more and I don't have to worry about.
Exactly. Right. So even the subscribers at the edge, they do not lose a lot of dBs
Right.
in the antenna gain, right? The wider, the better. Now, if you're using the same frequency, either in the back or maybe in other sites in the same area, then you have to worry about the interference that you generate with the other sites.
The neighboring sites.
The neighboring
Okay,
sites.
okay.
So in that case, the beam width plays a different role. Maybe you want your beam width to be smaller, so you have a smaller footprint
Right.
where your interference is going,
Right.
because now you can reuse the same frequency somewhere else,
Right.
and the interference signal is not arriving at the other site.
Right.
So the answer is it depends on where you are using the same frequency.
But then, in summary though, for frequency reuse in 90-degree sectors, this is a perfectly good antenna.
Yes.
Right. And then if you want to use, and there is no detrimental effect of using this in a frequency reuse environment.
Correct.
And then if you want to use this also in situations where you want to cover a 120-degree sector, it's a great antenna.
Yes.
But at a 120-degree deployment, you would not want to do frequency reuse. Or if you do, you may have some interference at 120 degree sector?
Well, it depends where you're using the frequency. If it's another site, it's important to consider where the sector is pointing to. You want the sectors to point away from each other, not facing each other. So you have to see where the interference goes, and the 90-degree beam width in a 120-degree sector may help you focusing the interference away from another sector that you have deployed with the same frequency.
But fundamentally also, typically we don't say use 120-degree for frequency reuse.
Correct.
Is that right? Okay,
Right.
okay.
Also, if you have 120-degree sectors, you will have 3 sectors in a site, right? So with 3 sectors, you don't reuse on the same site the same frequency, would be A, B, and C. At that point, you need to worry about where those frequencies are used in another site and where, which direction they're facing.
So complex topic, but hopefully between our conversation, you teaching me, we're able to convey some of the knowledge. But fundamentally what you're saying is that the subscribers sitting between 45 and 60 degrees, the drop-off in energy, we have managed to keep it not as drastic.
Sure.
And therefore, you can still get a good link sitting between the 90 and 120-degree sector. And that's why we're saying you can use this antenna successfully in a 120 or 90. While an antenna designed only to be a 90-degree, we would see a drastic drop after the plus minus 45, thus making it unusable, another antenna in a 120-degree sector.
Correct.
So it boils down to that.
Exactly.
Okay, great. We're wrapping up in terms of time, getting kind of close, so maybe just a few more touch points. The 2 other things that we highlight on this antenna, we spend a lot of time talking about front to back and 90 and 120 use, is the fact that we have good null fill.
Yes.
And I'm going to give my view on null fill and you can verify, but we're essentially talking kind of the balloon example. As you're building a balloon, you're going to, if you squeeze it, it'll come out in one direction but have different shapes in others. An antenna pattern, and if you may show a typical antenna pattern, right.
So this is an antenna pattern in the azimuth direction, which means in this direction.
In this direction, right.
And this is an antenna pattern in the elevation, which is the vertical direction. Like
so in this pattern, essentially, and unfortunately, when I look at a green screen, I don't know exactly where this is. We'll have to figure out how to do this better. But in vertical, I'm a long tower. My AP and antenna is looking this way. I'm on top of a mountain. And I have subscribers really close by. If there's a null, meaning there's a deep gap in my coverage because I don't have energy, that's essentially a null. That means all of a sudden, even that subscriber is so close, they're not going to get the performance they need.
Correct.
And that's where null fill comes in. So an antenna that does the best job of squeezing that balloon and still able to provide coverage right below has good null fill.
Correct.
And our patterns clearly indicate that we have good null fill.
Yes, so you want to make sure that when you move in elevation with the negative angle going down, then you don't have some angles where the gain is significantly lower and then comes back up. Otherwise, any subscriber that's in that direction will see a much lower antenna gain, which is not what you want. So the null fill is very important. Another thing to notice about our pattern is that there is a down tilt. If you
electrical down tilt, automatic down tilt.
So if you look at the pattern, the peak of the gain is not exactly at 0 degrees, it's about 2 degrees down. This is also very important for keeping the interference under control. If you have a down tilt, then you project your energy on a smaller footprint, and it makes it easier to reuse the same frequency in another site nearby. Of course, you can always use an additional mechanical down tilt. You can just tilt the antenna, but even if you install it straight, the antenna already has a couple of degree down tilt, which also helps.
And this is a very important topic because if you happen to be replacing an existing antenna with a Cambium Sector Antenna, please pay attention to the built-in down tilt because our previous generation antennas did not have a 2-degree electrical down tilt. So putting it exactly the same way is not good because you will suffer from performance that you had before, even though this antenna is a far superior antenna.
You have to see where the subscribers are and how close or far they are. If we
but don't assume the same way you installed the last antenna is going to work in this case.
You have
so
to
look at the pattern.
That's different. Correct.
Okay, we're just about running out of time. As always, thank you everyone for joining. And Lucia, thank you so
Thank
much
you.
for coming in and talking about a very complex topic. As always, we encourage our audience to go to our community, ask questions, post comments on Facebook or YouTube as you watch the video, and we will do our best to come and answer that.
Sure.
And we will see you next Wednesday at 10 a.m. Central for another exciting topic. Thank you.